So let's start today's session. It's already 6:09. We're running late a little bit. So this session will be the last session for this course of advances in welding and joining technology in terms of live session. Um, so what we will do in session 8 is we will discuss something on something on metal transfer in welding, how it happens, different kinds of modes of metal transfer, what are their advantages, what are their disadvantages, and we will briefly touch upon something called 3D printing, or you can say it metal printing or additive manufacturing. What is the recent hot topic actually? So that we will briefly touch upon. So yeah, let us start. So what we will initially do, uh, we will initially stick to these fundamentals of metal transfer in arc welding and something called cold metal transfer, and then we will go through the questions as I do every session. Now, in terms of metal transfer, in arc welding, there are two different mode of metal transfer. What are those two modes? So, if you think of modes of metal transfer, in, let us say we are doing some gas metal welding, there are two different modes. One is this continuous mode, another is pulse mode, and then there is something called cold metal transfer, which is a new form of gas metal welding. So, uh, cold metal transfer is not if you think of that by the name, it's exactly cold, but that is not the true scenario. So what happens in cold metal transfer? It is in some lower temperature than the regular gas metal arc welding process. You know. So if you think of these modes of metal transfer, uh, in generally you will see that in gas metal arc welding, what happens? The transfer of molten metal from the consumable electrode to the weld pool. That's how it happens, right? The molten metal will transfer from the electrode to the whirlpool. Now, there are lots of secondary factors which are affecting those transfer of molten metal. You have the shielding gas, you have the composition of the electrodes, you have diameter of the electrode. All those factors will affect your transfer of molten metal from the consumable electrode to the whirlpool. And also you have this current, voltage, maintaining the arc gap. So those things are there. Now, if we are trying to figure out what are different types of metal transfer, there are three different types of metal transfer. Sorry, there are three different types of metal transfer. What are those? You have short circuit transfer. You have what else? You have globular transfer, something called globular, and then you also have split. There are these two different types of metal transfer happening. Uh, Now we'll go through one by one. What happens during globular transfer? If you see in globular transfer, what are some of the characteristics of those globular transfer? Here, welding current, if you see, this is actually low. Welding current is very low, but the arc gap is large. So when your arc gap will be large, droplet can grow very slowly. So what happens? Just visible.
Yes, sir.
Okay. So yeah, in globular transfer, my welding current is low. However, arc gap is very large over here, and because arc gap is large over here, droplet will grow slowly. So my droplets grow slowly. Correct? Now, how much time droplets will continue to grow? Droplets will continue to grow until your gravitational force. So there are different kinds of force. I mentioned one time in my earlier lecture, maybe I don't know if you can remember or not. So there are different kinds of forces, right? In our query. Now the depth of penetration, the stability of whirlpool, the amount of Federal loss, so those things depend to a large extent on this modes of metal transfer from those consumable electrodes. So, what are the various forces that cause the transfer of metal into the whirlpool? Now, the mode of metal transfer depend on this intersection of this force what I am talking about, right? And that governs the ability of welding in various positions. So, you have four kinds of forces acting in your alternator. One of those, you have gravity force, you have surface tension force, you have electromagnetic interaction also in the molten pool, and also you will have this hydrodynamic action. So these are some of different types of forces which are acting in a molten pool. Now, the force of gravity that may be a retaining or a detaching force depending on whether the electrode is pointing upward or downward. So this force is acting as a detaching force of that molten pool, right? But surface tension always tends to retain the liquid drop at the tip of the electrode. So these are opposing in nature, right? So this force depends on the radius of the electrode, something called capillary constant. So it's mostly on fluid side. So this can depend on this radius of the electrode and capillary constant, density of the liquid metal also. Those things depend upon these factors. Now, as I was saying here, you have electromagnetic force also. Now, electromagnetic force, in what other name you can think of in terms of electromagnetic force? I think you have heard of this Lorentz force, right? So, this force is set up due to interaction of the electric current, which is there in our body, with its own magnetic field. That's how electromagnetic interaction happens, right? Now, this electromagnetic force acts in the direction of the current when the cross section of the conductor is increasing in the direction of the current. So, I am saying that electromagnetic force in the direction of current, and this is true when cross section of the conductor is increasing in the direction of current. Right? So, similarly, the force acts in the direction opposite to that of the current if the cross section of the conductor is reducing in the direction of the current. So, this will be vice versa. Right? So, yeah, as I was mentioning, these are my four forces uh, which will always be acting during your molten metal transfer. Now, in the scaling for globular transfer, the droplet continues to grow until the gravitational force exceeds the surface tension force. And as soon as the drop attains some large size enough, and so the gravitational force becomes more than other drop holding forces, at that point of time, your drop separates from the electrode tube and is transferred to the whirlpool, right? So your gravitational force is surface tension force, right? And then the droplet transfer occurs when it attains some larger size than the electrode diameter, and then yeah. So that's how the globular transfer happen, and it of course will not be suitable any kind of making some intricate shape or some kind of 3D printing. These metal transfer is not suitable for that application. Then you will have this spray transfer. I talked about this globular transfer. Then you have spray transfer. What is there in spray transfer? Here, well, your welding current density will be higher than the globular transfer compared to globular, and your high weld current density will result in some high melting rate, and because of high melting rate, the droplets are formed rapidly, and also it can be pinched up quickly by high pinch force. So here your droplets will be of very small in size, and high welding current increases the temperature. Because it increases the temperature, it will lower the surface tension force, right? So welding current is high. That will affect in your temperature, and that will affect in your surface tension force. Correct? And basically, it is decreasing the resistance to detachment of drops. Yes. Decreasing the resistance to detach. Okay. And finally, you will have this short circuit transfer over here. Short circuit transfer. What is there in short circuit transfer? What is there in short circuit transfer? So in short circuit transfer, um, the liquid drop at the tip of the electrode that gets in contact with the weld pool before being detached from the electrode, and thus the arc is momentarily short circuited, right? Because you are contacting your tip of the electrode with the weld pool, it is getting short circuited momentarily. However, due to the surface tension and electromagnetic force that I was mentioning, which will always be acting as a opposing nature, the drop is pulled into the whirlpool and the contact with the electrode is broken. This re-establishes the arc, right? So it is kind of it is kind of uh, how should I mention? So yeah, anyhow, basically, it is happening like you are initially the liquid drop at the tip of the electrode that gets in contact with the whirlpool. You are basically initially detaching, making it short circuited, momentarily short circuited, and then due to some opposing forces like surface tension and electromagnetic, the drop is pulled into the whirlpool, and uh, then your contact is getting broken, and which again re-establishes the arc. That's how short circuit metal transfer happens. And here also, in terms of characteristics of short circuit metal transfer. Again, you have low welding current, and because you have low welding current, your droplet will grow very slowly. And as I was mentioning, the drop touches with the weld pool, short circuit takes place, and due to narrow arc gap, because you are having very narrow arc gap, your molten drop does not attain a size big enough to fall under gravitational force, right? And after short circuiting, what you are doing, your welding current flow increases abruptly. So initially, if you're plotting your current versus time, initially it was like this, and there will be some abrupt change in your welding current because you are short circuiting. So here my short circuit is taking place. So this is my current, this is my time. So in this region, there will be abrupt increase in my current and short circuit takes place over here, and that results in excessive heat generation during that short circuiting process, and the molten metal of droplet becomes thinner due to some low surface tension, and then your molten metal is transferred to the weld pool, and yeah, and then your arc gap is established that increases the arc voltage. So all these things are interconnected.
Sir, I have a question there.
Yeah.
Sir, short circuit transfer is a pulsation system. I mean that
Short circuit,
it
sorry.
is pulsating. short
Oh,
circuit system.
short circuit system
Metal
is
transfer characteristics is the pulse characteristic.
uh, it is kind of yeah, it can be repeated over cycle. Yeah, it is kind of pulsed. It's not continuous in them.
Sir, another question. Why is there globular transfer and spray transfer not suitable for printing?
So this- yeah. While your globular transfer and spray transfer is not suitable for printing, uh, your answer maybe in maybe in cold metal transfer power source. If you think of this cold metal transfer power source uh, or the metal transfer when you are using cold metal transfer, just a minute. Yeah, when you are using cold metal transfer, so cold metal transfer also works as a reduced welding current, and here you are extracting the weld wire at a short circuit condition. And in cold metal transfer, because you are retracting your weld wire at a short circuit condition, it ensures a drop by drop deposit, which is not the case for other metal transfer. So if it is drop by drop deposit, basically the wire is retracted, the instant current flows, and it breaks the arc. The metal droplet then detaches from the filler and fuses with the steel molten on base metal, and again the wire moves forward to create another arc. So, so this will ensure some intricate shape or uh, more or less heat affected zone during the process. Have I answered your question?
Yes, sir.
Mm. Okay. Okay. So we have talked about different kinds of metal transfer, like globular, spray, and short circuit. Then, as I was mentioning, in cold metal transfer, this is actually a part of gas metal, but in principle it works at um, retracting the weld wire at a short circuit condition, which ensure you are drop by drop deposit. And the main difference is in terms of feeding the wire. So what happens in gas metal arc welding or those metal transfer, the globular and spray transfer, there your wire will continuously moving forward into the weld pool, right? It will be continuously melting, and because it is continuously melting, it always forms some defect formation. Your melting is more, the crack formation will be more, porosity will be more, and because to eliminate those defects, cold metal transfer came into picture. So in CMT, cold metal transfer, we retract the wire, the instant current flows, and whenever we are retracting the wire, as I mentioned in the short circuit transfer, here also it breaks the arc, and because it breaks the arc, the metal droplet detaches from the filler. Of course, depending on your arc gap which have been maintained, and the metal droplet detaches from the filler and fuses with the uh, whatever material is still molten and also the base metal. And again, your wire will move forward to create another arc, and all these phenomena happen several times in each second. This is a very, it is kind of, again, this is also a pulse mode operation. Here, it provides a controlled method of a material deposition by sophisticated wire feed system at a very low thermal input, and in effect, it needs some high-speed digital control technology. Otherwise, uh, you cannot control that type of sophisticated wire feed system through some manual process. So, the robotic setup, some high-speed digital control technology is required for some WAM, or if you have heard of this term, where are additive manufacturing. So these things are needed in any kind of WAM setup. So yeah, these things are there. Now, what are the main features of CMT process? If you try to uh, jot down what will be the main features, of CMT process. So here your short circuit offers such low current corresponding to some low heat input, and then your short circuit occurs in a very stable controlled manner. Short circuit occurs in a stable controlled manner. Then during the metal transfer, as your droplet is detaching uh, thousand amount of time in a very single second, during the metal transfer, the current drops to near zero, and thereby any scatter generation is avoided. The current drops to near zero, and scatter generation is also avoided. And as soon as your metal transfer will be completed, the arc is reignited and the wire is fed forward once more with the welding current reflow. Right? So, my metal transfer complete, arc reignites, and wire is fed forward. Here, another droplet. Correct? Now, your CMT welding electrical signal that consists of a three phase. So, you have a peak current where constant arc voltage corresponding with that high pulse current, and you'll have this ignition of the welding arc, which is very easy and to form those droplets. Then you have background current, which is a bit lower current level, and it prevents. Uh, so for to answer your question, uh, In CMP, this background current prevents that globular transfer of little liquid droplet and it continues until short circuiting occurs, right? And then finally you'll have this short circuiting option where your arc voltage will be zero, your wire is given backdrawing force, and uh, at that point of time, some kind of liquid fracture occurring and this transfer of material into the weld pool happens. So there are these three current levels, peak current, background current, and the short circuiting current. Right? Okay. So we will go through the questions one by one. Uh, we almost talked about different kinds of metal transfer and this cold metal transfer, of course, and we have only this additive manufacturing part remain. Uh, I will talk a little bit on these different kinds of additive manufacturing, what are different types of additive manufacturing, the basic mechanisms, what are the applications, what factors people uh, concentrate on to industrialize it successfully. So those things I will try to touch upon a little bit. Before that, let us go through the questions one by one and try to figure out which one will be the correct one. So what my question one says. If the following statement is correct about the cold metal transfer CNT compared to the gas metal arc welding. Go through the question once and whatever I feel just give me a correct one.
Option B is correct.
Option B. CNT is an advanced form of yes. CNT works at a higher welding current. No. CNT works at a lower welding current. Yes. And the option B is correct. You're correct. So here my option B is correct. Then you have next question. It says which of the following is correct about the mode of metal transfer and I is the welding current. Let's go through the four options and which should be the correct one.
Sir, here the option B is correct.
B. What is there in option B? 1 and 4. So 1 is for globular transfer current. This is yes, of course, more than the short circuit one. This is true. 2 is not true. Yes, this is also true. Okay. These are two. I will come back to this question 3 because this is something on this additive manufacturing part. Let's finish this part, whatever we have already discussed. Which of the following is wrong about the stream mode of metal transfer? In stream mode, it says it is tiny, it is low surface tension force, high melting rate, high surface tension force. It's wrong.
The wrong is the high surface tension force.
So I have already mentioned in spray metal transfer because your melting rate is higher, you are basically because of increase in temperature, you will have low surface tension. So high surface tension is unknown. So here option D is correct. In the cold metal transfer process, what is the role of the phase short circuiting? It is also had mentioned during the examination. Um, of course, it will not ignite the welding arc. Short circuiting is basically to promote this liquid structure and transfer of the molten droplet into the weld pool, right? Option C. Agreed?
Yes, sir. Yes, sir.
I will come back to question 6. I will come back to question 7, question 8, question 9. Okay, everything is on additive manufacturing. Okay, so let us let us spend some time on. I don't know how much I will be able to explain everything. Uh, but let us spend some time on this different types of additive manufacturing. This is a huge area. This additive manufacturing, specifically this metal additive manufacturing. Now, hmm, so as you know, there are different kinds of additive manufacturing, like liquid-based additives, then you have powder-based additive, then you have solid-based additive. In liquid-based, you have stereolithography, jetting system. In powder-based, you have heard of those terms like selective laser sintering, electron beam melting, selective laser melting. Then you have, uh, yeah, those things are there, and then you have in solid-based additive manufacturing, you have fuse deposition modeling, then you have something called feed stacking technology. So lot of additive manufacturing techniques are there. So um, mostly there are 3 to 4 technologies which are industrialized in a or should I say it has been revolutionized, right? So there are a lot of scopes in 3 4 additive manufacturing techniques like powder-based fusion, like selective laser sintering, selective laser melting, and DMLS. So you have this DED process, direct energy deposition. I will try to touch upon those things one by one, uh, not in detail, but in brief. So initially, let's talk about a little bit on this stereolithography process. So uh, stereolithography process is not kind of, this is a laser-based process, of course. It works on this photopolymer resins. So here it reacts with the laser, the photopolymer resin, and then you will cure it to form a solid, right? It is generally accepted as being one of the most accurate 3D printing processes, excellent surface finish. But what are the limiting factors in stereolithography? You will require some post-processing steps, and also the stability of the materials over time. It gets deteriorated over time. It may be more brittle uh, when you spend more time on the process, right? Now, in any kind of 3D metal printing, you will have this 3D geometry of the object, right? You will have some CAD design or CAD file. So what the software in the additive manufacturing machine will do, it will slice it with layers. So that's how it decides the layer thickness. And then your CAD file will be converted to some .stl format, and then all the data will be saved to 3D printer, and whatever your CAD design or whatever the STL file, it has been converted. In that path, it will if you are talking about this metal additive manufacturing, the melting and solidification will be very precise in that path, right? Now, now, why 3D printing is kind of coming very popular in the sense why that is happening and why um, it is basically you can think it of like it is eliminating some conventional manufacturing process like casting, like forming, those things. Because the main reason is the ease to make the component. As I was saying, the 3D model made using the modeling software, the CAD software, which is sliced using that slicing software, right? And the slicing software converts that 3D model to multiple 2D layers. So 2D drawing is much easier to make compared to the 3D component. So what AM do, it uses that as an advantage and prints each of the 2D image as layers in certain direction, making an extrusion, right? Thereby making the component in 3D. As simple as that. So due to this, the most complex designs can be made easily using 3D printing. And this is also time saving when compared to some conventional method. As in the conventional method, the same component would need multiple different processes, which will always be cost efficient, right? Now, coming to this uh, different kinds of additive manufacturing process, you have this fuse deposition modeling or powder bed fusion or 3D over conventional methods. So, PBA for powder bed fusion, here your power source, what it will do, first melts the layer of powder that is sprayed in the container, which is vacuum sealed or filled with some inert gases to make sure that powder particles do not react to its atmosphere. And yeah, once the layer has been scanned, so there will be some mechanism of friction which will move at a fixed amount based on how thick the layer should be. And there is some coater which will coat over a new layer of powder. And in the powder purification process, the beam size is limited. And maintaining a huge amount of powder is very difficult. Correct? So here your beam size is very limited. And this process requires some post-processing to remove the extra parts and basically smoothening, finishing at the surface, in the surface, right? And the parts are normally built on a flat base plate to ensure the powder is sprayed evenly across the bed in powder bed fusion. So the most common laser powder bed fusion methods are selective laser sintering, selective laser melting, direct metal laser sintering. So those things are there. Now, instead of laser as a source, you can think about electron beam as a source. So at that point of time, it will all be electron beam melting, right? So in both the methods, the energy is used to melt the materials and bond them together using some okay, leave it. So in both the materials, in one case you are using laser as a heat source, and for another case you are using this electron beam as an another heat source, right? Now, I don't know if I can draw it or not. Let's try to draw this. Uh, we have some space over here. So if we try to draw this EDF process, I don't know how much I will touch it. Still, so let's say this is my laser source. Okay? I am having a laser source and having a lens is over here through which you can basically some terminating lens to focus out. Then you have this mirror and then your laser beam is uh, irradiating uh, over your powder bed. Okay? So this is my laser beam and there are three compartments actually. One is this we call it powder overflow compartment. Then you have bead compartment and then you have powder sheet compartment. So these are my three compartments over here. So this is my piston as I was mentioning over here. Some piston mechanism. So yeah, this is my piston and at each compartment you will have this kind of pistons. Also you have this one, but this is a filling compartment. So I'm filling my powder. Here. Okay. Somehow I have managed. So what I was saying in powder bed fusion, um, this can produce some high resolution features, of course, and components with some dimensional controls and the ability to fabricate parts with some internal channels and basically it provides two key advantages over traditional manufacturing techniques. Now, as states over here, the basic components of a powder bed fusion that contains an enclosed chamber with a heat source, either laser or electron beam. You will have a scanner. You will have a powder bed. Um, you have a metal supply bed. Again, as I was mentioning, some recoater arm and usually some inert gas supply. Right? Now, yeah. So this powder bed fusion system form the powder bed by continuously rolling the metal powder from the metal supply bed onto the build platform. These are compacted cylindrical particle thick layer between 20 to 60 micron, in the range of 20 to 60 micron. And the build platform provides the necessary mechanical and thermal stability for the build This will increase the quality of the printed part, of course. Okay. Hmm. So this is something on this powder bed fusion. Then you have this DD method, the direct energy deposition. Now, if we try to draw this direct energy deposition, let me draw a schematic. Okay. So in direct energy deposition, we are having a laser system. And we have some beam guidance system which will guide your laser beam to concentrate on a certain region. And then you have this lens over here. This is this is my laser. This is getting focused. Local spot, and we'll have some kind of deposition here. We have some kind of deposition here, which is connected to a powder supply. This is my powder supply region. This is our carrier gas, and this is making this deposit over here sample. So that is a simple schematic of this DD process. Now, here also your power source first melts the powder or where in DD based on the fitting mechanism. So this process is assisted with some shielding gas to ensure the feed doesn't react with the atmosphere. So unlike powder bed fusion, multiple axis deposition and multiple mixture delivery, those things can be used in this processing, direct energy deposition. And this process can also be used with the conventional manufacturing process for finishing, machining, and yeah, the process is mainly used for some aerospace applications. This is due to its dimensional freedom. So there is no size constraint over here in DD. And the materials used in these systems such as titanium, unicornal, paper, industry working on this establishing this DD process for different kinds of materials like as I mentioned, titanium, unicornal, SS, and more. So the two types of DD methods based on the feed are powder DD and wear DD. So I talked about this wear additive manufacturing. So that's where this wear DD uh, that's where this wear DD comes. Now the main difference between DD and TDS is that in DD, in direct energy deposition, the material is directly fed into the melt pool. In DD, into the melt pool. And that is not the case for powder bed fusion, right? Now, as I was mentioning, the advantage of DED is that there are no size constants due to uh, due to the lack of powder bed, and compared to TDF, DED has a lower resolution and mainly used for making bigger 3D models with slightly lower resolution. Now, the methods of DED can also be based on source of energy. So, again, you have this laser powder direct energy, you have this laser wire direct energy, you have this arc wire direct energy deposition, you can have electron beam direct energy deposition. So those things based on your changing your power sources, right? The only energy source possible for the powder feed mechanism is a laser. As for the wire feed mechanism, the energy source possible are laser, electron beam, electric arc. So those things are there, right? Now, yeah. So, so can you tell me a little bit on difference of this laser melting versus electron beam melting? What will be there? So, if you see the selective laser melting system, uh, that use a motor-driven mirror system to deflect the focused laser beam at different points on the powder bed to develop the structure. Whereas in electron beam melting system, it generally requires a vacuum in the base chamber since the main free part of the electrons at sea level in atmospheric pressure is only a few microns, right? So you have to have some vacuum chamber over there. Now, I have already talked about this working principle of electron beam. So this is similar to that of a scanning electron microscope actually. I don't know of this ACM or not. So what happens in scanning electron microscope? So here your electrons will be extracted from a metallic filament through a high electrostatic potential or some accelerating voltage. You'll apply some accelerating voltage and you extract the electrons from a metallic filament, right? And which are then deflected with this then it is some kind of magnetic coils. So it will then be deflected through a column to rupture the beam in the designated areas. That's how it works. That is the working mechanism. Now, laser and electron beam BED systems are generally quite similar, but the main difference stems from the build atmosphere. Build atmosphere in the sense either we can use argon or nitrogen that works for laser system or for electron beam system. This is vacuum only. Yeah. Uh, let me try to uh, let me try to figure out if we have any other differences. Like for laser powder bed fusion system, the substrate can be heated and maintained at some approximately 90 degrees C. So this is reducing the effective temperature gradient between the main pool and the substrate. So you are basically preheating the substrate, right? So this temperature gradient and the subsequent cooling rate that has been directly linked to the local microstructure development of the melt pool. So yeah, people are working on those areas also. And for EPBF system, the electron beam power bed fusion, the power bed platform is heated to 50% of the powder melting temperature to greatly reduce the thermal variance experienced during NP. So, um, yeah. So, what I talked about DD, there are a lot of things I have mentioned. Yeah, in DD is also, we call it this laser engineered setting. So, DD is also termed as lens. Laser engineered net setting. So, again, let us recapitulate what I have talked or again repeat. So, it's basically using the focused thermal energy from the heat source to melt and fuse the feedstock or powder what you are trying to deposit and then deposit it onto the substrate, right? So due to the lower accuracy and it requires post-processing of the printed part, CVD is much less common, you can say, or people are working on the recently to make it, to make it suitable for industries and yeah, so that the post-processing is much less, accuracy is much more. Those things are there. Those are secondary factors, but yeah, the mechanism is really interesting. So, the advantage for DD printers is the ability to produce large part volumes uh, or some repair purpose. So, you can repair the damaged parts by using them as a substrate or build plate in contrast to the powder bed fusion system. And also, the DD system is offering you more flexibility in terms of heat source and feedstock. So you can use laser, arc, EV heat source, uh, whatever you want to use. That can be used in the DD system as well metal wire or powder for the feedstock. Right? Those things we have already talked about. And what advantages? DD can add additional kinematic degree of freedom to improve the quality and complexity of the printed part. Right? So your processing time is also much quicker than other methods such as PDS and the mechanical properties can finely tuned by controlling the microstructure to control this thermal gradient as I was mentioning by preheating and those things. Um, yeah, so I talked about this EDF, I have talked about this GD. We have some other system, but I have I have not introduced to this binder jetting system. So this is also there something called binder jetting system. This is also a metal 3D printing technique. Uh, if you think of a binder jetting system, this technology has provided a lower cost printing system, which is capable of some producing complex geometries out of various metals and ceramics. Now, working principle of a binder jetting system is kind of similar to powder bed fusion, uh, in that the printer head selectively deposits a liquid binder onto the powder bed for each layer. So, in simple terms, we can think it up like that. So, here also a powder reporter lays down a fresh sheet of powder for the next layer to be binded. And after deposition, depending on the machine And binder chemistry, the binder can be either partially cured between layers, giving sufficient strength to be removed. Um, yeah. So either even partially cured between the layers uh, after printing, or it is required to completely dry out, where it can be removed from the powder bed system and then cured up some more amount of hours. Now, once all the layers have been deposited, uh, the part, we call it the green part, uh, the green part that needs to be processed further. So, this printing technique can involve several post-processing methods depending on the machine, which are not usually found in DED or PBS system. So, you need to do curing, you need to do depowdering, you need to do sintering, you need to do handling with treatment, some kind of infiltration process, finishing process, lot of post processing is requiring binder jet system. Now, here your furnace is held at some specific temperature between from 650 to 70, in the range of 650 to 70, to allow the binder to burn out before before ramping up to this sintering temperature for the specific alloy. For different alloys, we have different sintering temperature, right? Before that, the furnace need to be held at some specific temperature. Now, one of the main drawbacks for binder jetting is relatively low density of binder jetting system. Relatively low density, the process is able to obtain kind of so and produce relatively low dense product. Actually, there is lot to talk about. Uh, so the basic mechanism in between this additive manufacturing and welding are almost similar. Okay, let's talk about a little bit on this on the physics of the weld. So how can we characterize the weld pool? And once this is done, we'll go back to the question part again. There are 26 questions, which is very obvious that you can answer out. So before that, let us spend a little bit of time on this main full characterization in additive manufacturing, how they are done, what are the physics, those things. Now, as I said, the main pool formed during this additive manufacturing process is similar to that of uh, laser welding. I am mentioning laser welding because we're using lasers as a source in additive manufacturing, right? And this is an extremely important and complex process that determines the overall quality of the printed part. Now, the main pool characteristics are defined by numerous physical phenomena. What are those? If you are, if you're thinking in terms of laser welding, you will have ablation pressure. So let me write down. You will have ablation pressure. You will have vapor film effect. Then we have surface tension, gravity. Then you have Maranelli turbulence, recoil pressure. So these are some physical phenomena which characterize a male pool, right? Now there are two modes of male pool formation during laser or electron beam additive manufacturing. Which are those two modes I have already talked about in in welding courses. So there are conduction mode and keyhole mode. These are two different modes, right? This is also similar to additive manufacturing. So in conduction mode, you are locally melting the material to form a molten pool, and it is characterized by some shallow and wide mitigating defects. However, if the energy density is high enough, the keyhole mode can occur and form a deep, narrow pool where the metal evaporates, generating some recoil pressure and a capillary which is called a keyhole. So my two modes are one is conduction mode, another is keyhole mode. Now the processing parameters during the printing process, such as laser power, scan speed, those things can affect the size and depth of the keyhole generated and the collapse of this keyhole, right? So these things are shown to affect the porosity and other processing related defects. Now, let's say you are having some rapid solidification. What do you do? So any kind of rapid solidification will impede the vapor bubbles from leaving the melt pool, which leaves a keyhole pore within the part. Some researchers have shown that the Marangan turbulence and recoil pressure, those are the main driving forces uh, which cause the instability of this melt pool flow. And yeah, so during the melting process, the unmelted particles which come in contact with the melt pool that causes surface tension to pull the fluid at the surface towards the colder region and generating this causing reaction pores. I can understand this is a little bit complicated to digest, but anyhow, so yeah, as I was mentioning this, how this Marangoni turbulence cause this gaps and pore formation over a surface. And then furthermore, this recoil pressure that is generated by the evaporation in the keyhole, that also generates a vapor jet in subsequent fluid flow in the keyhole and molten pool, right? So those slow behavior happens in in a molten pool, same for laser welding and same for additive manufacturing also. Now, due to extremely high temperature generated by the heat source, the molten pool surface easily exceeds the material boiling point, so which can increase the pressure within the molten material. This is called the recoil pressure. So this recoil pressure is applied on the melt pool due to the vaporization of the metal, and that results in a high velocity vapor plume. So temperature is high. Let me draw in a simple sense. Temperature is high. Material can boil and vaporization leads to It's to what? High velocity vapor cooling. Yeah. Now, I have mentioned these two common techniques of laser melting in powder bed diffusion system. So, those consist of continuous wave and modulated melting. So, in continuous wave, melting irradiates the metal powder under a constant flux as it rasters each layer of the build, and during the process, the scan lines comprised of this molten and solidified melt pools will overlap on each successive pass, which partially remakes the previous raster line, right? In contrast to continuous waves, which I just mentioned, modulated lasers alternate between on and off position to create a series of short irradiation exposure uh, in the range of some order of microseconds. Here, each exposure overlaps with the former one. Okay, so there are two modes of powder bed fusion. One is this continuous wave, another is modulated wave. Okay, now your laser power and spot size is highly dependent on the machine also. Now, yeah, the power is the source of the heat flux, right? Your laser power is your source of the heat flux, which is transferred to the metal powder, while the spot size is the diameter of the focus beam, which can be altered depending on the focusing system. So, and what is scanning speed? Scanning speed is the velocity of the laser spot, correct? Which traverses across the beam. Now, for for continuous laser melting, uh, for this one, what happens? This is defined by the distance. This is defined by the distance traveled within a certain time step, while in a modulated melting, it is defined as the exposure time, the scanning speed. So, what is my scanning speed? Velocity of the laser spot. That's the this is velocity of laser spot, right? Now I have two different kinds of laser source. One is continuous, another is modulated. Now here for continuous one, this is the distance traveled within a certain time step. And here the time is equal to the exposure time for whatever time it is exposed to the system. Correct? Now, what can be different common defects in metal additive manufacturing? So, if you think of in terms of welding, you can have porosity. Same things happen in additive manufacturing also. You can have porosity, which is extremely common defect in additive manufacturing, right? Lithium battery mechanism during layer deposition, those are driven by a temperature gradients, capillary forces, gravity. porosity is very much obvious in any kind of additive manufacturing. Then you can have lack of fusion during the printing process. Then you can have residual stress, gap formation. Those things are there, right? Now, cracking in additive manufacturing is largely attributed to the thermal residual stress that is generated due to this large temperature gradient and rapid solidification. So, those physics are coming again and again in additive manufacturing also. Right? Now, let us go through the remaining questions, and then we will finish the session over there. I have talked a lot of additive manufacturing in a very short period of time. Anyhow, let's go to the question and try to figure out which one should be the correct one, depending on the session. So my question here is that each of the following energy manufacturing process uses photopolymer resin to create a solid part.
Sir, option A.
Option A, 1 and 2, stereolithography, and why in selective laser sintering you want to use photopolymer resin? This is a metal 3D printing process. So yeah, I have not talked about this direct light processing. I am also not aware of this method. Anyhow, direct light processing uh, is mostly used for this polymer resins also. These two are metal purpose, right? Selective laser sintering and sheet stacking. So 1 and 4 are correct. Agreed?
Yes, sir.
Yes, we have done. Yes, we have done. Which of the following additive manufacturing process extrudes molten plastic through the nozzle? So yes, we have not talked about this fused deposition modeling. There you will use this nozzle per se. So this is also known as fused filament fabrication. This is also a kind of additive manufacturing process, and this comes in the realm of this material extrusion. So FDM builds parts layer by layer, selectively depositing melted material in a predetermined path, as simple as that. And what does it use? It uses this thermoplastic polymers that come in filaments to form these final physical objects, right? Now, okay, let us leave it. Actually, there are working mechanisms also in fused deposition modeling. So you will have this filament spools, you will have some support filament, you will have some main filament, and support structure you will have. So yeah. If it's also draw some schematic, that will be better. So let me try to draw some schematic. So we have some kind of rulers. You have extrude the filament over here. Here you are extruding, and here you have this nozzle kind of thing through which thin plastic bits. This is a simple schematic you can think of. This thin plastic bits, and here this is a nozzle, right? We have this nozzle through which this plastic bits are coming out, and the liquid solid will be associated with some kind of heater and thermocouple to heat up this material during extrusion. Some heater and thermocouple. What is so here? CS deposition modeling. Uh, this is the process which extrudes this molten plastic through the nozzle. This is a very simple question. Can you give me a correct answer? This is the most common file type exported from the CAD software. You might have also introduced to additive manufacturing, I don't know. Anyhow, you are aware of those files. If you have done any kind of CAD modeling, you are aware of those files. So, which is the most common file type that needs to be exported from your CAD software like SolidWorks, and it needs to be exported for rapid prototyping of. This is also called rapid prototyping. Okay? This 3D printing is also called rapid prototyping. Which one will be the correct one? We form it to a .stl file, which needs to be exported. And then it needs to be given to your machine, and then this slicing software is there in your machine, which basically forms it into 2D and then makes it 3D by extruding. Then the next question was, choose of the following additive manufacturing process uses powder as a print material. Which uses powder as a print material? Quick stacking technology? No. Selective laser melting, it can use some powder, and direct metal deposition also can use some powder. Stereolithography is polymers, right? Two and three are correct. Okay. Then it says which of the following additive manufacturing process fully melts the metallic powder to create a solid part. You have laser sintering, you have laser melting, you have bleeding, you have fuse deposition. Which one of the following additive manufacturing process fully melts the metallic powder? Selective laser melting completely melts. and direct metal deposition. 2 and 4 are correct. If you are not agreed, you can mention over here. And then the last question says, which of the following anti-manifesting technology does not require a support structure during the complex part geometry? Which does not require a support structure? I have mentioned during my discussions. It's powder-based system, right? Powder-based system does not require a support structure. Okay, so if you have any question, you can ask me. Otherwise, we will finish up over here. Okay, bye bye.